The classic champion. Chemical rocket engines generate thrust by burning two propellants together in a combustion chamber at over 6,000 degrees Fahrenheit. One propellant is fuel, the other is an oxidizer that provides oxygen for combustion. The reaction creates superheated gas that expands and accelerates through a specially shaped nozzle, reaching exhaust velocities of 10,000 miles per hour. The nozzle converts thermal energy into directed kinetic energy using the de Laval design. Narrow throat expanding bell. Chemical engines produce millions of pounds of thrust. Saturn V's 5 F1 engines each generated 1.5 million pounds of force. Every astronaut launch uses chemical engines because nothing else can overcome Earth's gravity with sufficient power. The RS-25 Space Shuttle main engine operated at combustion chamber pressures exceeding 3,000 psi with temperatures reaching 6,000 degrees. Turbopumps inside these engines are among the most powerful pumps ever built, spinning at 37,000 RPM while moving hundreds of gallons of propellant per second. A Falcon 9 burns through 900,000 pounds of propellant in 2.5 minutes during first-stage flight. Chemical engines dominate spaceflight because they deliver maximum thrust-to-weight ratio, critical for fighting gravity during launch. The solid fuel giant. Solid rocket motors pack fuel and oxidizer pre-mixed into a solid rubber-like grain that fills the entire motor casing. The grain has a hollow geometric core, star patterns, circular tubes, or complex shapes that control burn rate and thrust profile. Ignition happens through a pyrotechnic charge that lights the entire inner surface simultaneously. The grain burns from the inside out at rates controlled by propellant chemistry and core geometry. Space Shuttle solid rocket boosters contained 1.1 million pounds of propellant each, burned for 127 seconds, and provided 71% of total liftoff thrust. Solid motors cannot be throttled, shut down, or restarted. Once ignited, they burn completely. This makes them simple and reliable, but dangerous if anything goes wrong. The grain composition is typically ammonium perchlorate oxidizer, aluminum fuel, and polymer binder. Burn temperatures reach 5,800 degrees Fahrenheit. Solid motors can be stored for decades without degradation, making them ideal for military missiles. The Minuteman III ICBM uses 3 solid rocket stages. Specific impulse ranges from 250 to 280 seconds, lower than liquid engines but acceptable given their simplicity and storability. The liquid fuel marvel. Liquid rocket engines store fuel and oxidizer in separate tanks as cryogenic or storable liquids. Turbopumps force these liquids into the combustion chamber at extreme pressures where they atomize, mix, and burn. Flow rate control means thrust control. Increase propellant flow for more thrust, decrease for less. SpaceX Merlin engines throttle from 40% to 100%. This control enables precision maneuvers, prevents structural damage during max Q atmospheric pressure, and allows powered landings. Common propellant combinations include RP-1 kerosene with liquid oxygen, used in Falcon 9 and Atlas V. Liquid hydrogen with liquid oxygen powers the Space Shuttle main engines, and Delta or full heavy. Hypergolic propellants like hydrazine and nitrogen tetroxide ignite on contact without ignition systems, used extensively in spacecraft thrusters and the Apollo lunar module. The engineering complexity is extreme. Space Shuttle main engines contain 50,000 parts. Turbopumps handle liquids at 423 degrees Fahrenheit while spinning fast enough to experience forces that would tear lesser materials apart. Liquid oxygen is stored at 297 degrees Fahrenheit. The injector plate contains hundreds of precisely drilled holes that create the optimal fuel oxidizer mixture ratio. One failure anywhere in the propellant feed system means catastrophic explosion. The efficiency monster. Specific impulse measures engine efficiency in seconds. How long 1 pound of propellant can produce 1 pound of thrust. Higher specific impulse means less fuel needed for the same mission, allowing greater payload or range. Solid rockets achieve 250-280 seconds. Kerosene-oxygen liquid engines reach 300-340 seconds. Hydrogen-oxygen engines hit 450-465 seconds in vacuum. The RL-10 engine used on Centaur upper stages achieves 465.5 seconds, among the highest for any chemical engine. The Space Shuttle RS-25 reached 452 seconds. This difference is massive compared to solid boosters. Exhaust velocity determines specific impulse. Faster exhaust means higher efficiency. Hydrogen produces the highest exhaust velocity of any chemical propellant because it's the lightest molecule. When heated, light molecules accelerate to higher speeds than heavy ones. The molecular weight of hydrogen is 2 compared to 18 for water vapor from kerosene combustion. But hydrogen creates engineering nightmares. Storage temperature is 423 degrees Fahrenheit, just 37 degrees above absolute zero. Hydrogen atoms are so small they diffuse through the crystal lattice of solid metal, causing leaks and hydrogen embrittlement that weakens structural materials. Tank volume is enormous because hydrogen's density is extremely low. The Space Shuttle external tank was 153 feet tall, mostly for hydrogen storage. The Electric Dream. Electric propulsion uses electrical energy to accelerate propellant ions to extreme velocities instead of chemical combustion. Specific impulse ranges from 1,500 to 10,000 seconds, up to 20 times higher than chemical rockets. NASA's Dawn spacecraft visited asteroids Vesta and Ceres using 937 pounds of xenon fuel. An equivalent chemical mission would require over 10,000 pounds of propellant. Electric engines operate continuously for years. Dawn's ion thrusters ran for 5.9 years of cumulative firing time, longer than any chemical engine could survive. The efficiency is revolutionary, but thrust is microscopic. Typical electric thrusters produce 2,500 millinewtons, roughly the weight of a few coins. You could stop the thrust with your hand. This makes electric propulsion useless for Earth launch, where gravity demands millions of newtons. But in space, without gravity or atmospheric drag, tiny continuous acceleration accumulates into massive velocity changes over months. Satellites use electric thrusters for orbit raising, station keeping against gravitational perturbations, and controlled deorbiting. Over 500 satellites currently use electric propulsion. The technology enables missions impossible with chemical engines because the fuel mass savings allow much greater payload fraction or extended mission duration. The ion thruster. Ion engines ionize noble gas atoms, typically xenon, by bombarding them with high-energy electrons in a discharge chamber. This strips electrons away, creating positively charged ions. High-voltage electrostatic grids then accelerate these ions to velocities exceeding 90,000 miles per hour, 3 times faster than chemical rocket exhaust. The ion beam creates thrust through Newton's third law. An electron gun neutralizes the beam after ejection to prevent spacecraft charging. The process is extraordinarily efficient because electrostatic acceleration can achieve much higher exhaust velocities than thermal expansion in chemical rockets. NASA's Deep Space One demonstrated ion propulsion in 1998, reaching asteroid Braille and comet Borrelly. Dawn's 3 N-Star ion engines each produced 92 millinewtons at 3/100 seconds specific impulse, consuming 2.3 kilowatts. The engines glow blue from ionized xenon plasma. Modern ion thrusters reach 3,500 seconds specific impulse. Next-generation designs like NASA's X-3 thruster produce over 5 newtons at 2,500 seconds, powered by 100 kilowatts. The limiting factor is always electrical power. You need massive solar arrays or nuclear reactors. Xenon propellant costs $3,000 per kilogram, so newer designs use krypton or iodine. The Hall effect thruster. Hall thrusters trap electrons in a circular Hall current using radial magnetic fields. This electron cloud simultaneously ionizes incoming propellant and accelerates the resulting ions outward through electromagnetic forces. The entire process happens in one annular chamber, simpler than ion engines that separate ionization and acceleration stages. Hall thrusters typically use xenon, krypton, or iodine propellant. They achieve 1,500 to 3,000 seconds specific impulse with thrust levels of 4,500 millinewtons, consuming 1 to 10 kilowatts. Lower efficiency than ion engines, but higher thrust and simpler design means lower cost and higher reliability. Over 2,000 Hall thrusters are currently operating in orbit. SpaceX Starlink satellites use krypton Hall thrusters for orbit raising and deorbiting. Traditional geostationary satellites use them for north-south station keeping, counteracting lunar and solar gravitational perturbations that would otherwise drift the satellite out of position. The Soviet Union developed Hall thrusters extensively, flying them on satellites since 1971. Modern Hall thrusters operate for 10,000, 50,000 hours before erosion of the discharge chamber walls from ion bombardment degrades performance. Magnetic shielding pushes plasma away from walls, dramatically extending lifetime. They're the workhorse of satellite propulsion. The plasma surprise. Magnetoplasmadynamic thrusters run thousands of amperes of electric current directly through propellant gas, creating plasma and generating powerful Lorentz forces that accelerate it outward. No separate ionization chamber, no electrostatic grids, just electromagnetic acceleration. Current flows through the plasma between a central cathode and outer anode, creating an azimuthal magnetic field. This field interacts with the radial current, producing an axial force that accelerates the plasma. The physics is elegant. MPD thrusters achieve specific impulses of 3,000, 10,000 seconds while producing several newtons of thrust, far exceeding ion or Hall thrusters. This combination could enable rapid interplanetary travel. The problem is power requirements. Efficient MPD operation needs hundreds of kilowatts to megawatts of electrical power. Current spacecraft solar arrays can't provide this. You need space-rated nuclear reactors outputting more power than small towns consume. consume. Japan's JAXA tested MPD thrusters extensively in the 1990s and 2000s, achieving exhaust velocities over 60,000 miles per hour. NASA research reached 200 kilometers per second exhaust velocity in laboratory tests. But without high-power space reactors, MPD thrusters remain experimental. They're waiting for power generation technology to catch up with propulsion capabilities. The nuclear option. Nuclear thermal rockets pump liquid hydrogen through a nuclear reactor core where fission reactions heat it to 2500-3000 Kelvin, approximately 4000-5000 degrees Fahrenheit, then exhaust it through a nozzle. No combustion involved. Pure thermal heating. This achieves specific impulses of 850-1000 seconds, double the best chemical engines, because you can heat hydrogen hotter than any chemical reaction allows. The temperature limit is set by the melting point of the reactor fuel rods themselves. Push beyond that, and the core disintegrates. Higher temperature means higher exhaust velocity means better efficiency. For Mars missions, nuclear thermal propulsion cuts transit time from 9 months to 3 to 4 months, reducing crew radiation exposure and psychological stress. NASA's NERVA program tested nuclear rocket engines from 1959 to 1973. The PUE engine achieved 845 seconds specific impulse. The NRX-XE engine ran for 115 minutes cumulative at full power. All technical goals were met. The program was canceled due to budget cuts after Apollo, not technical failure. NASA is now developing nuclear thermal propulsion again under Draco, planning orbital testing by 2027. The reactor core uses uranium-235 fuel elements designed to withstand extreme temperatures while maintaining criticality and structural integrity. Radiation shielding protects the crew. The ultimate dream. Nuclear pulse propulsion ejects small nuclear bombs behind a spacecraft, detonates them, and rides the plasma shockwave. Project Orion designed this system in 1958-1963 under physicist Freeman Dyson and others. Each explosion hits a massive steel pusher plate separated from the crew section by giant shock absorbers that smooth the acceleration pulses. Calculations showed specific impulses of 6,000-100,000 seconds depending on nuclear device design and detonation timing. A 4,000-ton spacecraft could accelerate to 3 to 5% of light speed. Mars in 3 weeks. Jupiter in months. Alpha Centauri in 130 years with 1960s technology. The team built a small-scale model using chemical explosives instead of nukes. It flew successfully, proving the shock absorption concept works. The engineering is straightforward compared to conventional rockets. No combustion chambers, no turbopumps, no extreme temperatures except during brief detonation moments. Scaling up was feasible. But the Partial Nuclear Test Ban Treaty of 1963 banned nuclear explosions in space, killing the project. Current international law makes nuclear pulse propulsion illegal unless built beyond Earth orbit using space-mined materials. The physics is sound, the engineering works, only politics prevents it. The air breather. Scramjets, supersonic combustion ramjets, compress incoming air through ram pressure at hypersonic speeds, inject hydrogen fuel, and ignite the mixture while airflow remains supersonic throughout the engine. They operate from Mach 5 to Mach 15 at altitudes up to 150,000 feet where sufficient atmospheric oxygen exists. No moving parts in the compression section because speed provides compression. The challenge is achieving combustion when air transits the engine in milliseconds at speeds faster than rifle bullets. NASA's X-43A reached Mach 9.6 in 2004, the fastest air-breathing flight ever. The Air Force X-51 achieved 240 seconds of scramjet flight at Mach 5. These speeds approach orbital velocity. Combined cycle engines integrate air-breathing and rocket modes, use atmospheric oxygen through the atmosphere, switch to onboard oxidizer in space. This eliminates carrying oxidizer for the first 90% of altitude, dramatically reducing fuel requirements. Single stage to orbit becomes possible. Multiple programs are developing this technology. Reaction Engine's Sabre engine pre-cools incoming air to 150 degrees Celsius in 0.01 seconds, then uses it in a rocket engine. Testing continues. Success would revolutionize space access by eliminating expendable rockets and enabling aircraft-like operations. The Photon rocket. Photons carry momentum despite being massless. When emitted, they push back on the source through radiation pressure. Solar sails exploit this using large reflective surfaces to bounce sunlight, generating micronewtons of thrust without propellant. Japan's Ikeros successfully demonstrated solar sail propulsion in 2010, flying past Venus. The Planetary Society's Light Sail 2 raised its orbit using only photon pressure from the sun, but thrust is extremely weak. A square kilometer of sail near Earth receives only 9 newtons of force. Beamed laser propulsion could provide much higher require photon flux. Ground-based or orbital laser arrays would push spacecraft equipped with ultra-lightweight reflective sails, keeping the power source off the ship. Breakthrough Starshot proposes using gigawatt laser arrays to accelerate gram-scale spacecraft to 20% light speed for interstellar missions to Alpha Centauri. A true photon rocket would use matter-antimatter annihilation, or powerful lasers to create intense directed light beams for thrust. Theoretical specific impulse is infinite because photon exhaust velocity equals light speed, 186,282 miles per second. No engine could be more efficient. The problem is power density. Creating chemical rocket equivalent thrust requires terawatts of power. Even with unlimited energy, photons carry minimal momentum per joule, so thrust remains weak. The hybrid combination. Hybrid rockets combine solid fuel with liquid or gaseous oxidizer in the same engine. The fuel is solid, typically hydroxyl-terminated polybutadiene rubber, while oxidizer like nitrous oxide or liquid oxygen is injected as needed. This design offers throttle control and engine restart capability impossible with pure solid motors, while maintaining simpler design than liquid engines. Spaceship One and Spaceship Two use hybrid engines burning hydroxyl-terminated polybutadiene with nitrous oxide. Virgin Galactic's suborbital spacecraft rely entirely on this technology. The fuel grain doesn't contain oxidizer, making it safer to handle and transport than solid propellant. Accidental ignition is nearly impossible. Specific impulse ranges from 240 to 270 seconds, slightly lower than solid motors, but acceptable given the safety and control benefits. Regression rate, how fast the fuel burns, is controlled by oxidizer flow rate, enabling thrust modulation. Challenges include fuel grain geometry changes during burning, affecting combustion efficiency, and lower performance than liquid engines. Several companies are developing hybrid orbital rockets. Gilmore Space in Australia is building a 3-stage hybrid rocket. The technology fills a niche between solid simplicity and liquid performance. The antimatter engine. Antimatter annihilation converts 100% of mass to energy according to Einstein's EMC2, the highest energy density physically possible. 1 kilogram of antimatter annihilating with 1 kilogram of matter releases 1.8 x 17 joules, equivalent to 43 megatons of TNT, about the same as the largest nuclear weapon ever tested. If that energy accelerates exhaust mass, theoretical specific impulse approaches 10 million seconds. A few milligrams of antimatter could power interplanetary missions. A gram could reach nearby stars. But antimatter doesn't exist naturally on Earth. Production requires particle accelerators, and current production rates are nanograms per year at costs exceeding $25 billion per gram based on modern accelerator efficiency estimates. Storage is equally challenging. Antimatter must be confined in magnetic traps, never touching ordinary matter. CERN stores antiprotons for days or weeks maximum. Scaling up by 10 orders of magnitude faces unsolved physics and engineering problems. Antimatter catalyzed nuclear pulse propulsion uses tiny amounts of antimatter to trigger fusion reactions in fusion pellets, potentially reducing antimatter requirements. This concept might be feasible within decades if antimatter production improves. Pure antimatter rockets remain theoretical, limited by production capabilities that may take centuries to develop sufficiently.